So thanks again to everyone that's joining me today. My name is Michael Middlemast. I'm the Category Manager for Renewables here at Seaward Group. I work out of our office here in Tampa, Florida, but we also have an office in the northeast of England, in the United Kingdom, where we manufacture and engineer all of our products, including our solar test equipment. I've been in the solar industry for just over 10 years. I began in a technical capacity designing residential systems and eventually moved into wholesale, ran a little wholesale business for commercial and residential systems, and then went on to work for a racking manufacturer for a long time, and then also for Zeva Solar, who are a subsidiary of the SMA Group. And that led me to my role here at Seaward around about 2 years ago. And I head up the product development, the marketing, and generally look after our renewables division. So I'm hoping that I can share some of my experiences with you, not only over the last 10 years, but also my experiences of working with 1500 volt systems over the last 6 to 12 months. And also I'll be focusing a lot on our Solar Utility Pro instrument. This is our new 1500 volt 40 amp test kit, which should be able to enable you to quickly and efficiently test PV systems at 1500 volts. So just before we start, I have a quick summary to give you, a summary of our disclaimer rather. This presentation cannot be considered as a replacement for any of the standards that I reference, and I've taken all reasonable care to ensure the accuracy of the information that I am providing. The reference figures and data have been taken from said standards, and they were current at the time that this presentation was created. However, we can accept no responsibility for any error or omissions within the presentations or for any misinterpretations by the user. For clarification on any part of this presentation, please contact me directly. And no part of this presentation is deemed a contract of training, and any persons performing electrical tests should be fully competent to do so. Really, I must stress this final line that safety to the operator of the instrument is really paramount to us. Also, just some housekeeping issues. There is a chat function within GoToWebinar. If you'd like to introduce yourself or network with the other attendees, that is always welcome. You can also pose questions to myself throughout the presentation, which I'll try and pick up as I go. And then at the end of the session, we should have 10 to 15 minutes left to answer any of your questions in the Q&A session as well. So I'd like to start us off by explaining how we got here and where the journey has taken us on the way to 1500 volt systems. When I began my journey in solar PV, we were operating around about 600 volts, much lower length of strings. And it was actually European EPCs that pioneered 1000 volt systems in the 2000s. And eventually, similarly, those same EPCs and others pioneered 1500 volt systems. And the first 1500 volt system that was connected was actually by Belectric in Germany in July of 2012. Belectric are a good company, good EPC project developer. They actually assisted us with the development of our Solar Utility Pro, our 1500 volt 40 amp instrument, and we specifically made that unit to fit their test requirement. Now, when we first started working with Belectric, we asked them, well, you've been working on 1500 volt systems. What have you been using to test these systems if there's nothing on the market? And they actually showed us, and this was really a large Frankenstein of an instrument that they'd had custom built. It was very heavy, it was very large, it needed to be dragged on wheels to the site, but sure enough, it was accurate and it did the job for them. So our main aim with the Solar Utility Pro project was to kind of shrink that down into a nice portable and safe instrument that could collect data easily. Now, while the benefits of 1500 volt systems may be apparent, and we'll cover those later, solar industry manufacturers are really trying to catch up right now. So we have inverter manufacturers. Some do have 1500 volt solutions, some don't. Most of them have them in their product roadmap. The same we have for combiners and connectors, and I think everyone's trying to catch up with the pace at which the project designers are moving, because certainly the cost savings for 1500 volt systems as opposed to 1000 volt systems are there. So certainly that's why we're putting them in the designs of solar plants, but we're not necessarily seeing the equipment catch up with those designs. And that is certainly true in the test instrument arena. For instance, right now, our Solar Utility Pro is one of the only 1500 volt solutions out there. It's certainly the most cost effective. There are others. There are one or two curve tracers out there, but they're very, very high in value, and some have not been released yet and are scheduled for release in May, and a little bit more on that later. So what standards can we follow with regard to 1500 volt systems? Well, right now, the answer is none, really. There are no standards we can turn to 1500 volt systems. So we should really, we have to adapt what we already have. So here in the USA, we obviously have the NEC, the National Electric Code, and we have Article 490 and 690. And they are making efforts on the code making panel to include 1500 volt systems. But we're not located on or in buildings listed. DC PV equipment rated at a maximum voltage of 1500 volts or less shall not be required to comply with parts 2 and 3 of Article 490. So what we can take from that is that while the panel is trying to set out a clear path for 1500 volt systems, there is really no regulation in regard to utility scale and ground mounted systems right now for 1500 volt. Now that helps us in some ways, so we're not hampered by rapid shutdown requirements, etc. However, there are new challenges that we face, and I'm going to cover some of those in this presentation. So I mentioned earlier that we are moving to 1500 volt systems, and of course, I don't think we'll be moving backwards from that. But why are we actually doing that? Well, higher voltage strings means we can actually lower the current, and that results in a reduction of power loss on the PV system. So they're actually a lot more efficient. 50% longer strings than 1000 volt systems mean we have a lower balance of system costs. So we have less wiring, fewer combiner boxes, fewer connections. And this really helps us take a lot of cash off the price per kilowatt or per megawatt. And because of that, because we have longer strings, we're going to need larger inverters, and that's what's required for a 1500 volt plant. So we actually have less inverters, but they're larger, so there is a cost saving there as well. And overall, with lower balance of system materials, fewer inverters, fewer connections, overall, this lowers the labor cost of an installation. So this is the reason we're moving to 1500 volt systems, quite similar to the reason we moved from 600 volt to 1000 volt systems. So a quick comparison here of the differences between 1000 volt and 1500 volt systems. And this is taken from a great website. This is solarprofessional.com. And you can see that on the one hand, a 50% increase in system voltage nets us a 33% reduction in the number of source circuit combiners. On the other, 1500 volt combiners presently cost 40 to 50% more than 1000 volt combiners. So actually the price of a 1500 volt combiner is more than a 1000 volt combiner. However, when we look at it holistically, the number of combiners required and the average number of strings per combiner stays the same at 24, but the number of strings overall is really reduced, and the number of module per strings is increased. So overall, this really brings our cost down quite significantly with regard to balance of systems and with regard to labor. So this is all well and good. We're going to save a lot more money. We can become independent from government subsidy and tax credits because we're offering a very stable return on investments to our client without the need for any kind of governmental assistance. But we do face new problems, and again, with any new technology such as this, we need to overcome those problems. And some of the the issues that we've identified so far here at Seaward is that lowering the current of the strings is good, okay? But what happens is I'm finding that more of those strings are put in parallel into a single fuse in the combiner box. And that means we have a greater safety risk. So rather than having one or two strings in parallel into a single fuse, that may be at 8 amps each, so we've got a total of 16 amps short circuit current at that fuse. We might have 3, 4, 5 strings at 6 amps, and again, you can see the inherent safety risk there that we have a lot more current at the fuse, not to mention the increased voltage. That was why with our Solar Utility Pro, we decided that we wanted a very high rating on the short circuit current side. So this unit will operate at 40 amps DC, 1500 volts DC. So what that means is you can test multiple strings in parallel quite easy with our instrument. And I do suggest that if you're looking for 1500 volt test equipment, you should really look for a high maximum current rating. So for instance, there are other instruments on the market which can IV curve trace at 1500 volts, but they only do it at 10 amps. Now that is not so useful to us, particularly if we're dealing with combiner boxes. Also, another issue that we're facing, and not relating to test equipment, but fewer inverters mean we're lowering the cost, but we're actually putting all of our eggs in fewer baskets. So this means if one inverter goes down, we lose a lot more generation than on a 1000 volt system. So this is something to be aware of when we are designing our PV systems. Also, higher strings are more susceptible to the dreaded PID, and I'll cover that a little bit more on the next slide. And this is something we really need to be aware of. And the good thing about our instrument, the Solar Utility Pro, is that because we're testing for open circuit voltage and we're comparing that open circuit voltage to what our expected value should be, we're comparing our measured value to our expected value, we can really tell if a system is being affected by PID just from that reading alone. That, you know, sometimes a curve trace is really unnecessary in that regard. For those of you that would like to learn a little bit more about PID, this presentation isn't about PID, but there are lots of resources online. So I've just put together a little summary here. It's basically when a module's voltage potential and leakage current drive ion mobility within the module between the semiconductor material and other elements of the module. Basically, the energy is trying to escape, whether it be into the glass, the racking system, the aluminum frame. This is when we get PID, and this deteriorates the photovoltaic effect within the cell, and it really greatly affects the efficiency of the panel. So what we're finding is these days that a lot of 1500 volt panels, modules, are coming with this stamp of PID free. For instance, Q cells have this, Trina have this. So when you're looking to pick solar panels for 1500 volt installations, be more kind of aware of the PID and the effect it can have on your system. So this probably won't affect, in fact, it definitely won't affect any new system you're commissioning. But if you're going back to a legacy system and you need to test it and you see issues with the voltage, most likely that is going to be PID. And that's why we're seeing more and more solar panels coming through that are glass on glass, using rubber clamps. And this really insulates the photovoltaic cell so it's not affected by PID. Or less affected, I should say. So we've discussed there the history of 1500 volt systems and why we're transitioning to those type of systems. So I'd like to really get into the nitty gritty of how we test and what we're looking to test with these systems and what unique issues we face against 1000 volt systems. And again, just to reiterate that your safety is absolutely paramount to us. Okay, if you think you get to a site and you think you have some issues with safety and you don't want to connect, my advice to our users is don't connect if you don't feel safe. So with regard to safety, we're facing, as I say, higher voltages, higher currents. So arc flash is a real serious concern. So we should always be prepared for the worst. So we should wear rubber insulated gloves. They're our first line of defense. Cover those with leather gloves. Wear the correct PPE. We need eye protectors. We need impact helmets. We should have our arc flash rated jeans and jackets. And we should also ensure that we perform an on-site evaluation with regard to safety before we begin works. Don't just go there, open up the combiner, connect, and push the auto button to test. Okay, we really should be prepared. And it alarms me sometimes the people that I work with who are not so aware of the dangers that they face when working inside the combiner box. And if you have any fears at all, it's probably best not to work in the combiner and work at the string level if you can. Let me see, have I skipped a slide? No, here we are, the Seaward Solar Utility Pro. So I mentioned that we've been hard at work developing a 1500 volt instrument, and this is it. This is the Seaward Solar Utility Pro. It's housed in a Pelican case. It's very rugged. It is an official Pelican case. We didn't use any kind of fake. And the instrument is very easy to connect, both in the combiner and at a string level. It will give you open circuit voltage, short circuit current, irradiance, ambient temperature, and cell temperature. We then take this data and we import it into our reporting tool, and this will tell you if the system is performing in line with our expected standard test condition values. So for instance, if your measured VOC is different to your expected VOC, this could indicate that we have shorted bypass diodes, PID, wiring and connection issues. And also, if your measured short circuit current is different to your expected ISC, this could indicate that we have ground faults or micro cracks, or perhaps a combination of faults. The instrument will also check polarity when you connect it, which is one of the biggest problems I see with regard to commissioning systems. So this Solar Utility Pro is really born from our experience with our previous instruments, our PV150, our PV210. They're rated at 1000 volts, 15 amps. And one of the biggest problems I had with those instruments was that my users were overcurrenting the device. So they were putting more than 15 amps through that device. So that told us that, right, we really need a high upper limit for this instrument. So this is why we went for 1500 volts at 40 amps. So before you begin testing, please ensure you have the correct equipment for what you need and don't take something to site which doesn't have a high enough rating. This is the unit itself, and you can also see what is in the kit. We have the irradiance meter, the temperature probe. We give you cables to be able to connect in a combiner box or at the end of a string. Also, we get a nice carry bag. It uses rechargeable lithium-ion batteries, and this is all included for $3,000 plus shipping, and it's available here from our office in Tampa and internationally. We also work quite closely with Solmetric. We're an official distribution partner of Solmetric, and there is a real difference between the Solar Utility Pro and the PVA 1500. The PVA 1500 is an accurate IV curve tracer. It can give you up to 500 points on the IV curve. It will also give you the temperature and irradiance that we need for our STC calculations, and it really gives you unprecedented measurement throughput and accuracy, and it gives us a real insight into the performance of the array. However, the instrument is quite large, okay, and also it needs an on-site PC to work, and also the instrument is approximately $9,000. So the way we kind of see things and the way the partnership works is that you could give the Solar Utility Pro to all of your test crews and perhaps have one or two PVA 1500s that you use to really get down into the nitty-gritty of what the problem is. So whereas the Solar Utility Pro does not require an on-site laptop, it's very rugged, it's quite light in comparison, it'll give us VOC, ISC, temperature, and irradiance. The Solmetric is larger, it will give us the full IV curve trace, but it is also a lot more expensive. The other issue is the Solmetric PVA 1500 is not actually available right now. As of this presentation, we expect it to be released at the end of May, and this doesn't really help us with regard to systems we have to test right now. So if you do have a requirement for 1500 volt testing, the way to go would be the Solar Utility Pro. But if you do wish to place a pre-order for the PVA 1500, we are accepting those. Demand is quite high. So prior to performing any of the electrical tests, we should really do visual inspection. And this is a site out in the UAE. It was a very large site. It was 260 megawatts. And I was testing on this site and they were having a lot of problems. And you can see just by looking at it, the panels are very dirty. You can also see the tire treads just down to the left of the panels. And what was happening is, as they were cleaning the panels, this was kicking up stones and actually cracking the panels. And this was causing us big issues. So you might think, well, I'm going to see that. I don't need to do a very thorough visual inspection. The question is really about where you are situated. So the combiner box that you're testing may have 24 strings in it, and the string you might be testing might be 200-300 feet down the table. Now, if you go straight to the combiner box and don't look at the panels, you're not going to notice that that panel has a crack in it. But by doing a visual inspection, we can kind of have in the back of our mind, okay, when I test that string, I know I'm going to see this. And also, visual inspection can really help us because we can pick up a lot of other issues. So that was the front of the panels. So we can see that they're dirty, there are cracks, there's perhaps spotted shading or uniform shading across the panels. But by looking around the back of the panels also, we can take a look at the wiring setup and the problems that we may see here. Now, again, on this particular site in the Middle East, the cables were left as they are on this picture on the right. Now, what was happening was dust was gathering at the ends of the cables where they were terminated. So they really need to be housed a little bit better, probably put up into the framing system. Now, in the desert, you don't get too much rain. But if this system was in, say, where I'm from, in the middle of England, and there's a lot of rain, the water is just going to run down the cable directly into the MC4, and that's going to cause us a lot of problems. It's going to cause a ground fault, and of course we can detect that ground fault using the Solar Utility Pro by comparing the measured ISC to the expected ISC, and that will indicate a ground fault for us. Another interesting issue we face on PV systems, particularly in again in England and here in the States, where we have installations that are maybe in a field or a brownfield site, rodents like to chew cables. So this is something we should really look out for. It's an odd thing, but it happens. And then also you can see in the top left-hand corner, we have an image of an MC4. Now this hasn't been crimped correctly inside, so the little metal plating inside hasn't been done correctly. And this can again cause an arc fault inside, which is causing the connection to melt. On a very serious level, this could be a fire hazard. On a less serious level, this is really going to drop out production of the entire plant. So this is why it's very important to have the correct test equipment. Again, not regarding kind of testing or test equipment at all, but from my experience working for a racking manufacturer, I'd like to highlight some issues that I've come across. You can see in the top right-hand corner, we have an image of an aluminum mounting system, and you can see the corrosion there. Now, these type of mounting systems, they're dipped in a chemical vat, and we get an anodized layer, and this gives us protection against high saline environments and against the elements. Now, if this layer isn't applied correctly, or for some reason it's deteriorated, then the aluminum itself is going to deteriorate. Similarly, for galvanized steel, and you know, if we have some perforations there for whatever reason, or it's not being protected properly, then we're definitely going to get some oxidization. So basically, metal will rust and deteriorate if we don't treat it correctly. And it's always good that we catch this before we begin our testing. One of the other reasons for this is, and I give an example here of a rooftop installation. If you get to a commercial rooftop or a residential rooftop and you see that there is a perforation in the roof and that is causing water ingress or any type of ingress, then we can't wait until the end of the day to tell the client that he has a problem with his roof. The reason for that is, if you spend a whole 8-9 hours working and then you come down and you say, oh, I've done all my tests, but did you know you have a crack in the roof? He's going to say to you, he or she, you did that. So if you see any problems with mounting systems at all, it's always good to take an image, record it, or tell someone immediately that you've seen a problem. Therefore, you won't get the blame for causing that problem. And that's something in particular we as PV test engineers need to be aware of. Just jumping back to our 260 megawatt site in the Middle East, I mentioned that they constantly have to clean the solar panels because of the dust, because of the atmosphere, you know, the nature of where they are. So what was happening is we were using these very big kind of tractors with brushes to clean off the panels. And again, the stones were being kicked up. But really, if you get to the site and the panels are dirty, you should really ask for them to be cleaned. If they can't be cleaned and the client insists that you carry on testing, we need to kind of take that into our STC calculation, our standard test condition calculation, and we need to put a factor in there for soiling. And our software will allow that. But also, we're not going to get good results when the panels are dirty. Basically, it amounts to shading of the panels, and that's going to drop our short circuit current down, and it's not going to give us a good idea of where we're at. One interesting thing to note, just as an aside for this site, we had to dry clean the panels. So if we mixed water, obviously with the dust, that's just going to make mud or clay on the panel. So this system was really hard to clean. So here are some images of a before and after, and you can really see the dramatic difference that the cleaning has made. And this really is an extreme example. However, on the after photo, you can still see some of the dust settled on the panels. And again, that's going to drop down our test results and probably not give us the most accurate reading. So we really do need to take this into account. Whenever you're testing, it's a good idea to take pictures, to note what the conditions were, and this sort of thing to add to your test results. It's no good just giving the client, okay, here's a bunch of numbers, and we need to give context to those numbers. The good thing about our instruments is that if you can do a test before you clean, and then clean the modules thoroughly, and then test again, we can show the performance increase to the client in real terms. This means we can set ourselves up for a real long-term cleaning and maintenance contract. So another issue that I face, particularly again in my hometown, my native land, the UK, is low light conditions. So I was asked to test this site here in Lincolnshire. I believe this was June, maybe earlier, but still we had very, very cloudy day. There was just no way we were going to get good results. We were getting less than 100, 150 watts per meter squared on the irradiance meter, so we had to postpone this. So again, if you're asked to test when the sun isn't high in the sky, okay, when we don't have good irradiance, we're not really going to get good results. So we should really try and push back to the client and say, listen, I understand you're under time pressures to get this testing done. However, we really do need to wait till the conditions are more optimal. It's also vital that we mount our irradiance meter correctly, and working in the industry and with the Seaward equipment for quite a while now, I've found that some people do not mount the irradiance meter correctly. So they will lay it on the floor, they won't connect it at all, they will put it on top of the panels that they're testing, and again, that's going to cause a big shading and hot spot. So I would recommend using a mounting bracket to mount your irradiance meter. And also this goes the same for the temperature probe. So we really need to get accurate temperature data in order for us to correct voltage to STC, because the open circuit voltage is directly affected by the cell temperature. So with the temperature probe, for instance, on a 70 cell module, we should go 6 cells down, 3 cells in, and place it in the center of the cell. What this will do is it'll take away any additional heat that may be generated, because if we place it near the bypass diodes of the panel, generally heat tends to accumulate around this area. Also around the framing system, there's a lot of heat that accumulates around the aluminum frame. So we just want the temperature probe away from those hot spots. So we want a good inclination. That's the same inclination in azimuth. That is the same of the panels. We also want clear temperature readings. So I mentioned briefly earlier that we can compare our measured values to our expected values, and this will give us an indication of what is wrong with the system. So for instance, if I go to a site and I think, okay, I'm dealing with this string, just to give you some arbitrary numbers, each panel is 40 volts, VOC. There are 10 of these panels. So I should really see approximately 400 volts from this string. If I go to my test and I see 300, or I see less, or I see more, then that system isn't wired correctly, or maybe we have connection issues, maybe there is a shorted bypass diode. And the good thing about the Solar Utility Pro is that if you do connect to a system, it will tell you if there's reverse polarity. And also, if there is a faulty bypass diode, you should see the voltage swinging dramatically from low to high, low to high. That's the bypass diode kicking on and off when it shouldn't be. Similarly, with ISC, we can tell a lot if we compare our measured to our expected, particularly with ground faults and micro cracks. So if we're operating at 500 watts per meter squared, the back of the panel will tell us, okay, at 1000 watts per meter squared, you should see, let's say, 8 amps. So then if we do some calculations, we can say, okay, at 500, I should see 4 amps. Now, if I don't see that, if I see less than what I expect, then I know there's an issue with that string. I just had a question here from Cody. He's asked me, can I just repeat where the temperature probe should be placed? It's a good question, Cody. I'll just repeat that for you. As a general rule, I have found that if we go 6 cells down and 3 cells in on a 70-cell panel, that should give us a good location for the temperature. One thing I forgot to mention also is that we should allow it to acclimatize. So before we begin testing, we should leave it there for 30 to 60 seconds just to get up to the correct temperature. So you can see, just going back to this slide, that we can tell a lot just from the voltage and the current. Okay, we can indicate shorted bypass diodes, PID, connection issues, polarity issues, ground faults, micro cracks, or a combination of faults. And here at Seaward Group, we really do help you as well. So I'm always keen to discuss my clients' data. I'm happy to analyze data with you, and we also do provide on-site training where required. So generally, when we're dealing with these larger systems, we're going to be operating inside of the combiner box. And I'd like to describe the process for you for working inside the combiner box. So first of all, we've got all of our arc flash protection to the correct rating. We have the area clear from our work colleagues who are not in the test area. When we open up the box, we safely isolate the box, we open it up. And the first thing I want you to do when you open that box is just take a look at it. Okay, do a visual inspection of the combiner box. Make sure there's no faulty connections in there. Also, maybe smell, okay, because we can smell arc faults inside of the box. And even I've seen, I'm sure you guys have too, spiders in boxes or small mammals. So just make sure the box is free from obstruction and visually it looks okay. The second thing we're going to do, we're going to open up all of the positive fuses. Okay, so we're going to open up all of those positive fuse harnesses. Now, the very best practice that I advise is to take out all of the fuses from those harnesses and put them to one side. Then take one single fuse, and we're going to use that for later. What we're then going to do is we're going to take our Solar Utility Pro, and we're going to connect one alligator clip to the common negative and one to the common positive. Now, bear in mind, right now, we don't have any string connected because none of the positive fuses are inserted or indeed inside the harness. So then we take the fuse that we kept with us and we put it inside the first fuse harness. We close it. We now have that string or whatever's connected to that fuse. That is then connected to our instrument. We should then see voltage on the instrument. We can push test. We wait for the test to run, doesn't take long. We push save. Open the positive fuse, take out the fuse, put it in the next harness, close, test. open, close, test, open, close, test, open, close, test. So very quickly, within 10 to 12 minutes, we can test a full combiner box very easily. The only kind of danger here that we're going to face is, and the reason I did ask everyone to take out the fuses from all of the harnesses, if we push 2 or more of those fuses together when we're connected to the common positive and the common negative, those strings are going to be in parallel. So remember, the maximum rating of the Solar Utility Pro is 40 amps. But if we exceed that 40 amps, very quickly, we're going to damage the unit. So that's something to be aware of. We don't want to parallel strings. Sorry, I should rephrase that. We don't want to parallel strings such that the short circuit current is greater than the maximum rating of the instrument. That makes a lot more sense. So as you can see, with this method, we can very easily and quickly test a full combiner box. So we're testing polarity, open circuit voltage, short circuit current. We're also gathering irradiance and temperature. And once we get that data from the instrument, we're going to see how they compare to standard test condition values. String level testing is a lot safer, I find, because we're not dealing with the full combiner box. Arc flash protection is not so much of an issue. However, we should still be very careful. We can connect directly to the MC4 cables, or we can use the alligator clips to connect to the end of the PV cable. So we have 2 methods there. We also provide probes, so you can use probes into the positive and negatives. Or if we open up an inverter, we just need to be careful because that inverter will hold a capacitive charge, and we just need to make sure that that charge has dissipated before we connect our instrument, or else we could get some problems there, and we could damage the instrument. We could have an arc. If you are using the probe tips, either in the combiner box in the top of the harness or inside an inverter, just be very careful not to pull the probe away during the test, because again, you're going to pull an arc, and that's going to damage hopefully just the unit and not yourself. Some good tips for taking good measurements, just to recover these, we need to take these measurements from a clean array, okay, whenever we can. This will give us the most accurate results. And we should also retake measurements with large deviations from our expected values. So I mentioned earlier, you've got in the back of your mind, okay, well, I've got 10 panels. It should be 800 volts. I'm actually getting 600 here. That seems to me like there's a problem. I'm not just going to save that and give it to the guy in the office. I'm going to try and prove a negative. Okay, I'm going to try and prove that negative result. So if you see a large deviation from your expected values, test it again, test it again, test it again. And if you can repeat that large deviation, that confirms to you that there is actually a problem with the string and it wasn't just something errant in the test. Again, we need to ensure that the irradiance level is really stable. Okay, so as well as being in the same inclination and azimuth as the panels, we also really need to make sure that we have a nice steady irradiance. So what we do with the Solar Utility Pro, you can actually see the irradiance on the screen. It's being transmitted from the smaller irradiance meter. So when you're running the tests, I just want you to watch that screen and make sure it doesn't swing wildly. So for instance, a cloud goes overhead or the apprentice wanders by the panels. Okay, we just need to make sure that we don't have a large deviation. And I would say anything above 10% of the irradiance is a real large deviation. And again, we need to make the temperature sensor acclimatized to the panel, and we should be 6 cells down, 3 cells in, right in the center of a cell. So when you're connecting the cables to the instrument, make sure that we make a really firm connection. Okay, we don't want any gaps in those connections because gaps mean arcs. Okay, we should also keep the device very clean. If we get dust and dirt in there, particularly on this site in the Middle East, which I've discussed, this is going to make the buttons stick. It's going to get underneath the screen. It could potentially cause arcs inside of the unit. So we really need to keep it clean and keep the lid shut when we're not using it. Whenever possible, store the instrument at room temperature, okay, in a smoke-free environment. I've had instances where, particularly out in maybe Minnesota where it's very, very cold, that the instrument has been left in the van overnight or the truck. And then when we come to test it, there is a fault because it's not actually operating within its operating temperatures. So we just need to be very careful. Similarly, with very hot environments, electronics don't really like very hot environments, right? So we need to keep it within the operational temperature. And I would also advise to keep spare batteries with you at all times. So I have a question here from Brian. He asked, do you have a good technique for detecting and locating a DC arc fault in an array? That's a very good question, Brian. It really depends where the arc fault is. If the arc fault is with the MC4 connections or the sun clicks or whatever it may be, that's probably quite visual. You'll be able to see that. However, if it's kind of within the junction box, that is more difficult to detect because it might not become so bad that it's caused damage to the junction box yet. Similarly with PV cells, you know, if we have some problem with the filament that holds the cells together, if there's some kind of arcing in the PV cell, that is also hard to tell. However, I would just advise take a close look at your expected short circuit current to your measured short circuit current. And if you have a large deviation from that, then you should be able to say, well, I know that that string does have a fault, particularly maybe an arc fault, because my short circuit current is not in line with my expected values. Another good technique, and we can pick up a good IR camera for $300 to $400, is to just do some thermography, some handheld thermography. So I've tested a string. I see that my ISC is not in line with what I expect. Okay, I'm going to pull out my camera and just quickly run it over the panels, and you should be able to see the hotspots on the panels themselves. So today we've covered where we are with 1500 volt systems and how we got here. I also covered the benefits of said systems and also some of the new issues that we face when testing these systems. I've also presented today the Solar Utility Pro, our 1500 volt test solution. And I would like to say that if you do purchase the instruments from Seaward Group, I can offer my advice and our engineering team's advice. So we can really give you expert advice, not only on the test process, but also on what the data means, how we can analyze data, and how we can help solve your problems on site. So I'd like to open up the floor now to questions. I hope there is some questions that I can cover. Okay, got a couple of questions coming through. First of all, one from Andre. Does the Solar Utility Pro have overvoltage protection in case of incorrect wiring? Yes, Andre. Actually, the unit is quite high rated at 1500 volts. So we have some protection inherent there in the maximum rating. However, as soon as you connect the instrument, it will check voltage. Now, if you are over the voltage, it will tell you immediately, and it will give you a warning sign. Now, depending on how much over the maximum you are, depends on if the unit will be damaged or not, but it will give you an audible and a visual warning that you've connected to a system that is over the maximum rating. I have a question here from Joe. Just to confirm, it looks like the Solar Utility Pro does not do insulation resistance testing, so I assume it is okay to keep the negative connected to a grounded inverter. That is absolutely correct, Joe. So we're not doing an insulation test or a mega test with the Solar Utility Pro, so we are okay to keep connected to the negative on a grounded inverter. That is absolutely fine, and we will be developing an insulation tester particularly for this section of the market, hopefully in the next 3 to 4 months. But right now, if you do need to run insulation tests on a 1500 volt system, there is nothing out there on the market that can do it as part of a kind of auto sequence. You would need a 5 kV tester set to 2 kV to run point-to-point insulation testing. Gail asks, will the graphics and slides be available? And also Hector is asking, will a video be available? Yes, both will be available. We'll follow up with an email with all of the slides, but also we'll be uploading the recorded video to our YouTube channel. I'm also more than happy to answer any of your follow-up questions. If you don't have any questions now, but you rewatch the video or watch the slides, I'm more than happy to help you with those questions you may have also. If you're on LinkedIn, please do feel free to connect with me. You can find me quite easily there. Again, my name's Michael. I represent Seaward Group, our solar division. So, if you do have any questions regarding our instruments, with both from a sales perspective or a technical perspective, please do get in touch. Right now, I don't see any more questions coming through. So, we have one more here from Joe. One more. Can you talk briefly about the data upload and analysis? Yes, certainly, Joe. Basically, we output from the Solar Utility Pro a CSV file. So basically a very simple Excel file. And within this Excel file, it will contain open circuit voltage, short circuit current, irradiance, and temperature details from all of the tests that you've taken. So what we do is we plug that into our Solar Utility Report. This is an automatic process, so you click Select File and import it in. Then you select the panel type that you're testing and the number of panels in the string. We can then add in offsets from STC. So for instance, I mentioned we can add in a variable there for soiling. And then what it'll do is it'll use the equations I mentioned earlier to show us how those values compare to expected values. So I have a question here. Do you use the IEC standards to convert to STC? Yes, we do. We use the IEC standard. Does the test unit have a fuse for protection against overcurrent such as parallel strings? Sean asks. Sean, the rating of the unit is at 40 amps, and indeed it does have a fuse. The question is just how much of an overcurrent is put in the inside of the unit. If it's just above the 40, we should be okay. We should be able to contain that within the fuse. If the overcurrent is such that it's quite high, it can basically blow right through the fuse and damage the internal workings of the instrument. Just circling back to the Solar Utility Report for a moment. This is the tool here. So I can import my my sample data set here. I will process the file. I could then select a panel, and we have a database of over 18,000 panels, and you can add in your own. We then select the number of panels in the string. We can also set our offsets, and what it will then do is tell us, okay, well, this string was in line with the VOC, but the short circuit current was not in line. And then we have some similar adjustment factors and acceptable limits. Hector has asked, where is this Solar Utility Report available? It's available on seawardsolar.com under the download section, or I can send you a copy of it via email. That's no problem. Christina has asked, speaking of mega testing, what is the minimum insulation resistance required ohms for the 1500 volt systems? The data table only includes 1000 to 2500 volt systems. It really depends on the method of insulation testing. So if you short out the circuit first, then you need a minimum of 1 mega ohm. If you don't and you're doing a point-to-point method, then we're looking at I believe 150 to 200. However, please, I think I would need to research that and get back to you with a correct answer. I don't believe those values are entirely accurate. So, Christina, I have made a note of that, and I will get back to you directly with an answer to that question. You're most welcome. You're most welcome. So if there are no more questions today, I'd just like to say thank you again for joining me today. And the Solar Utility Pro is available now. We have them here in Tampa, Florida. Demand is very high. So if you do have any 1500 volt systems heading your way in the next couple of months, I would advise to secure your test equipment in the coming days. And again, I'm more than happy to hear from you, your questions. Always happy to support our clients with regard to analyzing data and the problems you have on site. So if there are no more questions, I would really like to thank you. Oh, one more question here. One more question. How can you determine if the string has PID? Good question, Christina. The answer there is that what I mentioned about our expected values to our measured values. So if we're expecting 800 volts, for instance, and we only get 600 volts, okay, then that indicates to me that there is an issue. That's why it's really important that we get good temperature data if we're looking to analyze what the VOC would be, should be with regard to our expected values and with regard to STC. We can also compare different strings and different tests. So if we test when we commission the system, we can use that as a benchmark for our future tests. And also we can use the other strings around a problem string as a benchmark. So if I do 5 strings and 4 of them are all very similar results, and then the 5th one is way off, I know that there's a problem with that particular string. I hope that makes sense. Andre asked me, can I use the Solar Utility Pro as an IV curve tracer or just as a VOC ISC tester with the radiance and temperature compensation? No, the IV curve tracing is really a different test process. What we do is we short out the circuit and then we vary a resistive load on the string and take points current against voltage to give us the characteristic IV curve, the IMPP, the VMPP, and the max power point. If we're just taking the 2 endpoints, so short circuit and open circuit, we can't get a curve trace. So I think what has happened in our industry is that curve tracing has become a little bit of a red herring. Everyone thinks they need curve tracing. We need curve tracing. But I hope today I've proved that we can tell a lot just by open circuit voltage and short circuit current with those irradiance and temperature compensations. We don't need the full curve trace every time, because curve tracing, what we're trying to do, we're trying to replicate a laboratory test out in the field, and we're not taking into account air mass or lots of other things. So curve tracing kind of becomes this very difficult thing to replicate. So just from VOC and ISC, we can tell a lot about the health of a system and indeed verify the safety and the performance. Andre again asked, what does the wireless SolarLink look like? SolarLink is basically our term for the connectivity between the irradiance meter and the Solar Utility Pro, or our PV150 and our PV210. It doesn't really look like anything. It's basically just the term we've coined to represent the link between the irradiance meter, the wireless link between the irradiance meter and the test instrument itself. Just waiting for a couple more questions to come through, if there are any, and then we can finish up the session for today. If you did find the session useful, we'll be running the session again next month, and your colleagues are free to join me. They can sign up from the same link that you did. And also, if you have any questions and you would like to attend again, more than happy to do that. And then in June, we will start a new webinar series on a different subject, so please do look out from the notifications from us. And again, if you have a requirement for any test instruments, whether it be 1000 volt or 1500 volt, Seaward Group can really help you out. So with that, it doesn't look like any more questions are coming through. So I'd like to thank everyone that attended today. Thank you, Brian. Thank you, Andre. Thank you, Christina. Thank you, everyone that attended today and everyone that asked a question. Hector, Sean, everyone. So I hope everyone has a good rest of your week. I hope your testing goes well, and we will shortly follow up with an additional email, and you'll be able to find a video recording of this webinar on our YouTube channel. So thank you very much. I hope you have a great day, and we'll speak again soon. Thank you.